invited physicists to their mathematical seminars, and they both were deeply, profoundly interested in theology and philosophy. And a fascinated person for Professor Morin was Albert Schweitzer, and Julian Ławrynowicz, during his seminar in Bendlewo about 10 years ago, led us to Pniewy, where we could learn the spiritual and education heritage of Ursula Leduchowska. And I would like to concentrate in my presentation on two equations when complex numbers play a visible role. First, this is Euler equations dated 100 to 1748, and second, Schrödinger equation dated to 126, a mass constant Laplacian minus in x, it is space coordinates, of course, and potential and so I thought that complex imaginary unities are visible to all the viewers and also participants online. And I would like to say from the before saying about complex numbers, a few words about numbers. Months ago, it was published in weekly Niedziela, my article Liczenie po polsku, counting in Polish, where I explained the notion of numbers verbal, and according to me, two numbers are meaningful, namely 100 and 1,000. And we know that 100 is 100 in Polish and in all Slavonic languages. And like in Sanskrit, in Sanskrit and Hindu, we pronounce shata. In ancient Iranian, it was satem, and some half of Indo-European language in a half, usually east half of Indo-European languages, this numeral is pronounced similarly. And other, And so that these languages are called Satem languages. And this means that ordinary people in European tribal groups counted up to 100, and as for Western Indo-European languages, they are called Canton ones from the Canton meaning 100 in early Latin. And as for 1000, it is quite different situation, because we have in part, of course, Tysiąc in Russian and Ukrainian famous Tysiacza, but also English 100, German 100, Swedish 1000. So why that is so? Because up to 1000, people counting to up to 1000 belong to maybe said distinguished and small social groups. And let us come to complex numbers. In almost all languages, and Polish is exception, we say complex. In Russian, complexy. So, and we have complex, and Polish name, Zespolone, is specific and accurate, because if we literally translate it into French, it would be said that the nombre d'ensemble. And as for urojone, the situation is most interesting, I think, because in all other languages, almost all, they are called imaginary numbers, even in Czech, imaginati. The difference is about Russian and Ukrainian, mnimie numbers, but the problem is in this English linguistic relations that the verb, word and verb, urojony, uroić, is specifically Polish and has weak equivalents in other languages. Because, for instance, in Russian, as I know, mnimoje, manie and mnimoje is close to not to be imaginable. And in Polish, the meaning is somewhat connected with psychiatric context, yes? So, and let us come to the question, the mathematical approach about numbers. And I refer to the book of American authors, all Gerban and Austin and Olmsted, counterexamples in analysis, kontrprimiery w analizie in Russian edition, and what is maybe paradox, but what is the most, I think, natural and fundamental structure in mathematics, because referring to real numbers, the field of real numbers, we can introduce the notion of ordered ordered fields, namely an ordered relation is to define and box that an ordered equation demands a split in two parts to this. It is a sum of disjoint sets, and the axioms are that I think that it is understandable. That the multiplication by minus one changed the that belongs to other part, and then plus the condition and what this proof is similar. Let us take the imaginary unity I. So suppose that it belongs to F plus. So I V belongs to F as well. But what is I? To 3 it is minus I, so it must belong to F minus. That is a contradiction. So second possibility is that I belong to F minus. So then I 3 and F minus means that it is equal to minus I, and then I3 is equal to I, which belongs to F plus. And contradiction again. So what I can express this fact verbally, that complex numbers are not self-sufficient to in mathematics on very elementary and basic level. Yes? So, and this is in contrast to real, to the field of reals. Yes? So, reals are, maybe say, much better than complex numbers. Yes, okay? Vocally? No. Ah, yes. Yes, okay. So let us, but well, you said players, it may be a little up. Is this?
Measured by the camera.
Not. So I must, so let us say that. And let us come to the history of mathematics in several last centuries. And what we can say about numbers, it is difficult to study all historical cases and precedents, but I think that it may be said that before Euler, and Euler lived before Euler equations, complex numbers in mathematics were episodic. It was they were algebraic episodes when second, third, fourth order algebraic equations were taken into account. And for instance, it is almost sure that in works of Diophantus, Cardano, Tartana, complex numbers more or less explicitly appear. But they were only, I see, isolated cases. And as for Leibniz, who lived and worked shortly before Euler, he wrote his general paper, short booklet, Historia et Oligocalculi Differentialis. And he made a general sketch about calculi differentialis and about integration and differential calculus. But in his works, I found only case of dealing with second order equations and with specific coefficient. And the great change were done when Euler wrote and edited his work in Introductio in Analysin Innitorum. And André Weil's editorial idea was to translate and edit this historical choral book as one of Springer volumes. And the development in exact science, especially in mathematics, astronomy, and math physics, was initiated when the work of Copernicus, De Revolutionibus, appeared. And the time period between Copernicus and Euler can be divided in two parts. About 1960 28. And they are quite different because it was a lazy development made mainly by, in Polish we could say them rachmistrz, by in numerical domain, and the heroes were Rheticus, because Copernicus adjoined to the Revolutionibus for decimal place tables of chords, and chords are double signs. And Rhetic made a far jump forwards because their jump was from 4 decimal places to 15th ones. And 20 years after death of Rheticus, it was so near the end of 15th century, these tablets were edited, and then it was a problem how to multiply and divide, let's say, to 15 ciphers numbers. And then it was the work of Napier to make first approach to logarithm, and his work in MATLAB, Modifici logarithmorum canonis descriptio. And his Napier logarithms were almost homomorphic, so that Napier logarithm of multiplication plus some correction. But this for Joachim Kepler, it was no problem about correction because he used successively and effectively Napier tables to in order to prove by counts here's the third law of movement of planets. But Briggs observed that there is the following formula: logarithm in the decimal logarithm Napier logarithm of 1, this is minus Napier logarithm of electron. And in this way, the Napier that tables of decimal logarithms were tabled and were recognized, but the problem was in natural logarithms, because it was recognized by some answer that similar looks the graphs of 1 by x, and the field under the graphs of logarithms that look similar, but and it was and so the period from on this scale, because let me here was a period of some mathematics, and we can say 2 years. Why? Because in this book of advance, the historical development of calculus, we can read at the beginning about John Napier, and his polemical tract contained proofs in Euclidean fashion that the poet was the Antichrist and that the world was due to end in the year 1786. So, and as for astronomer who developed Copernicus, Tycho Brahe, he was in a duel, he lost a tip of nose and it was replaced by a piece of, by a substitute consisted of piece of silver. So obtain. And but and it was that maybe contained in a limited domain, tedious development, but after Brick's a stormy development in astronomy and mathematical analysis ensued, and so we have, for instance, that Newton proved and calculate power series of sine, cosine, but other mathematicians counted power series. And this domain Bernoulli numbers, and for instance, students of mathematics do not solve the solution of Maclaurin series for tangents, for instance, yes? And so this developed was very strong and stormy, because on the other hand, this connection between fields up from after logarithm, natural logarithm function, and e2 its divert, it is an integral, and this functions as advanced, right? This relationship was not fully clarified until the time of Euler in the 18th century. And maybe this article But maybe, okay. So we see that, so it was a turning point, not inflection, but what was a change after emerging Euler's Introductio in Analysin Innitorum. In the preceding state of mathematical analysis, differential and integral calculus, order was established, and all earlier literature is not comprehensible to even qualified mathematics. But Euler's book, Analysis Innitorum, is clear and comprehensive. So it was, now it is a number of beginning of analysis as a mathematical analysis, as we learn and study it, and what our main point of this version. Then number E was established, and as we see, this equation was adjoined to mathematics whose literature was built with very complicated formula. So, and of course, then, and initial point of this development was astronomical, because it was work of Copernicus for its needs, trigonometrical tables and logarithmic tables were done. And later, then also planetary beginnings can be discerned in Bessel functions, because they were they were discovered by Bessel and Jacobi in order to exclude perturbation of Saturn orbits by Jupiter. But let us pass to the to this century, to this preceding 20th century, and just to Schrödinger equation. In quantum mechanics, they were similar. If we look at early 20th century and first papers about quantum mechanics due to Bohr, Zohar, and Heisenberg, they are not readable for us. But if we take our end the book of Schrödinger in physical review, an undulatory theory of the mechanics of atoms and molecules, it is clear, and we can point out analogy with the work of Euler. And for instance, here we see that this is time dependent, and all spectra, yes, and this energy spectrum of hydrogen atom, so we can know it is clear to see introduction of complex numbers, the ordering road, and also the I counted it is a spectral line of hydrogen and hydrogen atom, and the observed are, as I counted, 91 and implying from Schrödinger equations 57, and it looks very similar. And what is in quantum mechanics I would like to in final part to say about quantum chemistry and Penrose ideas. And as for quantum chemistry, but I think, as Professor Lucian Piera from chemistry from Faculty of Chemistry in Warsaw University said me what a rapid development in quantum chemistry is. That here we had about 100 energy levels and values and eigenvalues and nothing. The time independent Schrödinger equations were it is output of theory that the complex and imaginary numbers disappear, but when only ground energy level is taken into account by quantum chemists, and so up to about 3,000 electrons system can be recognized and studied and will approximate by quantum chemistry. If we would like to have more exact equations, then up to at about 100, then we should apply relativity improvement taken from coming from Dirac equations, and then complex numbers reappear. And if we consider the case of when the systems are in magnetic fields, then also complex numbers reappear, and the number of electrons in systems and studies is about 100, not more. But what is the present state of the development of quantum mechanics now, and about the fantastic ideas of Roger Penrose, mathematical frontiers and perspective. Robert Penrose believes that complex numbers will be crucial in future development of mathematical physics. And he believes that twistors will play a crucial parts in quantum chemistry hidden in quantum gravity, hidden dimensions, and Big Bang. And I doubt it. Why? Because it would be strange if complex numbers which turn out to be insufficient in mathematics, as I have proved, would be crucial for mathematical physics. So and I think that other people interested in physics and mathematics may share such opinion.
What do you think about the hypercomplex, about the next step, about the hypercomplex numbers?
Oh, because this is a domain which I am not familiar, but Penrose says about bispinors and other, and as for this, and of course, but let me say, quaternions are less self-sufficient than complex numbers because they are non-commutative please. Octonions are non-associated. And because I don't know, I must admit, I don't know hyper definitions of hypercomplex numbers, but I think that this problem concerns such objects which seems in some sense more artificial than complex numbers and the real numbers, of course. And look that if we develop quantum mechanics, we can come back to real numbers in many times as quantum chemistry recent developments shows us.